Welcome back. So the last time we were in the process of proving that C1 implied differentiability. That is, if you take a function whose partial derivatives exist at a point, and in fact in a neighborhood of that point, and the partial derivatives are continuous on that neighborhood, then this function is differentiable on that neighborhood. Okay. So in the process we arrived at the following inequality, from which point we shall continue the proof. Okay. So remember that this was proven to be less than h plus so this is the second term, and we've added and subtracted this derivative term. All right. Okay. So at this point, what can we do? Well, first of all, as h comma k goes to 0 and 0, what happens? If you look at this term, as h comma k goes to 0 comma 0, this goes to 0. Why? Because we have assumed the induction hypothesis that G being C1 implied that it was differentiable, and the fact that G was differentiable at the point A comma B implies that indeed this goes to 0, right? In fact, by the way, our theorem stated something a little stronger. We said if the function is C1 on a neighborhood, then it's differentiable on that neighborhood, right? Whereas we seem to be only considering differentiability at the point A comma B, but this A comma B point is arbitrary. There's nothing special about it, so the same argument would apply, right? But anyway, so this goes to 0 by induction, basically, induction hypothesis. Right. What about this? Okay. Why would this go to 0? As h goes to 0, why would this go to 0? The reason is one variable calculus, right? We have assumed that not only do the partial derivatives exist on a neighborhood, but they're also continuous. So in particular, they do exist on the neighborhood. If they exist on the neighborhood, over here we are simply fixing this. So this is by one variable calculus, it goes to 0. The question is, what about this? Okay. So for this, it's not too difficult, but the intuitive reason is we have assumed that the derivative is continuous. So as k goes to 0, if k is very small, right, this is very close to this. That is the point. Okay. So that's what we'll use here. So first of all, the third term is less than what is the third term? It's this times h0 divided by mod h. In fact, it's equal to, but this is less than well, at the cost of putting a constant c in whatever norm you want. So notice that this is basically, what is this? This is simply the difference between two one variable derivatives, namely df by dx1 at a point times h minus df by dx1 at some other point times h, right? So the h can be pulled out and it cancels out with this. The rest is obviously less than c times the norm of the full derivative linear map, right? Whatever norm you choose, you'll pick up a constant c, right? Now the point is, now we can use this Lagrange's mean value theorem, for example, or any other result to conclude that this goes to 0 as k goes to 0. For instance, by continuity of df by assumption. Right? So this this will then prove what we want. Yeah? Okay. So this proves the result that C1 implies differentiability. Right. Now we need some properties of differentiability. So what properties of differentiability am I alluding to here? Basically, in one variable calculus, how do you differentiate functions? You have rules for derivatives, yeah? You have the sum rule, the product rule, the quotient rule, the chain rule, etc. We need to prove their analogues in more than one variable calculus. It's not too difficult because notice that the derivative matrix is basically a collection of partial derivatives, and partial derivatives are one variable beasts. So we don't really need to reinvent the wheel much. The only trouble, if you wish to view it that way, in more than one variable calculus is you need to do a lot more bookkeeping. So for example, as we shall see later, even the statement of the chain rule is a rather tedious affair as opposed to the one variable calculus version where it was much simpler. Right? So we need to do a lot of bookkeeping, but there is nothing shocking going on in most of these properties. There will be a very deep property that we'll prove or at least state much later. That's called the inverse function theorem. But other than that, the other properties are to be expected. Yeah. So let's look at these properties. In fact, let's assume f and g are from Rn to R, but honestly there is nothing that we will lose if f and g are vector valued functions as well. But nonetheless, for now, just so that our bookkeeping is more pleasant. Right. So how does one prove this? Bear in mind that proving that the partials exist and the partials add up is one variable calculus. The only non-trivial affair here is differentiability is not a one variable phenomenon. Okay? So we have to use the definition, but then the proof is almost just a slightly vector valued version of the proof of the one variable calculus one. Okay. So what does it mean for this to be differentiable? The linear approximation must hold. Right. So this is less than. You simply use the triangle inequality. I'm sorry, I'm not using the vector signs, but it's understood. For example, this should have been a vector, right? This should have been a vector and so on. But I will omit them often. This is standard practice and it's expected to be understood within the context. Right. So this of course goes to 0 as h goes to 0. Why? Because we know this goes to 0, we know this goes to 0, right? So that's why the sum goes to 0. As a consequence, this also goes to 0 by the sandwich rule. So that means by definition not only is f plus g differentiable, but the derivative is the sum of the derivatives. So in one shot, yeah. Remark. So the same proof works for vector valued functions. Okay, we'll just look at each component and apply this. You don't even need to use the same proof. You can just apply the same theorem to each of the components. Okay. Okay. F times g is differentiable at A. This is the, if you wish, this is the product rule with derivative right. Now note that stating this rule for vector valued functions is going to be slightly more painful using matrices, right? Because this of course makes sense for each component, but if you look at them as vectors, then it is best indeed to look at each component and apply this rather than stating a more general rule. Okay, but this is sort of an exceptional situation. Later on, we will see that it is actually helpful to look at a vector valued function as a vector valued function and to look at its derivative as a genuine matrix, because we'll be multiplying matrices. Okay, but for now, we'll just state the product rule as it is. Okay. So how does one prove this? Again, the same proof as in one variable calculus, but right. So how exactly does this work, right? So if you take f of a plus h and g of a plus h, we know that approximately they are equal to their linear approximation, right? So we'll make this approximation precise by simply keeping track of the error terms. Okay, that's how we can do this. So this is, so before we proceed, maybe I'll write this here. This is the error in the linear approximation for the first function. This is the error for the second function. Now, delta I divided by h goes to 0 as h goes to 0. Again, these are vectors. Once again, I'm being rather cavalier here, but it's understood from the context. Yeah. Okay, so coming back to this, you simply write the linear approximation, but keep track of the error. There's nothing more mysterious than that. Just keeping track of the error in the linear approximation carefully, that's all. Okay, then once you keep track of it, then we can simply simplify the expression thus obtained. What will we get when you multiply these two? That will cancel out. Maybe I'll just write it. So when you multiply these two, this will get cancelled out. Okay. When you multiply this with this, right, that will cancel out with this. When you multiply this with this, then that will cancel this out. Okay, so what is left is multiplying f of a with this error term, right? Because we've already multiplied it with the other two. Likewise, multiplying the error terms with everything and multiplying this with the error term, as well as multiplying these two. Okay? So, what we can say at this juncture is the following, that maybe we'll first write this out. Okay? So, what is left is f of a times, maybe, so what I want to do is to use the triangle inequality here, divided by norm h, right? So, this multiplies with this, and then this one, g of a times delta 1 divided by norm h, yeah, plus delta 1 times dg of a h, right, by norm h, delta 1 delta 2 by norm h, plus the derivative of f multiplying delta 2 by norm h, and these derivatives multiplying each other. Right, this looks rather formidable, but it isn't. The reason is, what's this? This goes to 0 as norm h goes to 0. Why? Because this is equal to mod f of a times mod of the mod of delta 2 divided by norm h, and delta 2 by norm h goes to 0. So, if you multiply by mod f of a, that doesn't change. Likewise, this goes to 0. Okay? Right. So, we are left with the other terms, right? Notice, okay, so what strategy must be used here? So, this is delta 1 divided by norm h, this part goes to 0. The question is, what happens to this, right? This is not very difficult, despite looking very formidable. Let's do that here itself, yeah? So, what we can say is this juncture, delta 1 times by norm h times dg of h. Okay. Right. What is this? So, this goes to 0. This, we've already seen that this is less than some constant, maybe I won't write the precise form, some constant times mod h, right? This obviously goes to 0 as h goes to 0. Likewise, this also goes to 0 as h goes to 0 for the same reason, right? So we are left with these two terms, which we will continue in the next page. Yeah. So we are left with, so this is less than something which goes to 0 as h goes to 0 plus now we can of course add and multiply and divide by norm h. This of course goes to 0 as h goes to 0, right? And this also goes to 0. That's great. So this is less than something that goes to 0 as h goes to 0 plus, what about this one? So here we can say that this is less than c times norm h divided by norm h times another c times norm h. This goes to 0 as h goes to 0. In other words, we have successfully proven that this piece goes to 0 as h goes to 0, and therefore by definition of the derivative, f times g is differentiable with the derivative being given using our familiar product rule. Okay. Right. Now, if g of a is not 0, this is the, if you wish, the quotient rule. Is differentiable at a with derivative what you expect it to be, right? It's exactly what you would expect it to be. Notice that if I already tell you it's differentiable, knowing that the derivative is given by this is actually doesn't even need proof, simply because for each component you can simply use the one variable product rule or the quotient rule. The challenge here is proving it's differentiable, not proving this formula. That part is easy. Okay. All right. So without loss of generality, first of all, f is identically 1. Why is this so? Okay. I urge you to pause the video and think about it. We've already done this sort of a thing when we discussed the continuity of f divided by g. Okay, so that's why I don't want to repeat the argument. So all we need to do is look at 1 divided by g. For delta small enough, we see that for all norm h less than delta, g of a plus h is not 0, right? Why is g of a plus h non-zero? Because g of a is non-zero. Yeah, we know that g is assumed to be differentiable. Differentiability implies continuity, and by continuity, if g of a is non-zero, g of a plus h is non-zero for all norm h small enough. Okay. Again, you must be familiar with this argument by now. Even this is also from one variable calculus, the same kind of an argument. Okay. Right. So we look at the linear approximation as always. What's the derivative? It's expected to be this divided by norm h. Right. Now what must we do? Obviously we must bring this to a common denominator. This is not rocket science, right? So this is g of a minus g of a plus h divided by g of a times g of a plus h plus g square of a. Again, these are all vectors technically speaking, but as I said, I'll be rather cavalier and drop the vector symbol wherever it is understood. Now, how must we handle this term? As before, we want to use the linear approximation for g, right? Let me use a different color here to emphasize. So, this is what, by the linear approximation, so this is minus of the derivative of g acting on h, and what else are we left with? We are left with the error term, which we shall call delta 2 as before. So, what do we have then? Then we have this term and this term, this, and must be compared with this. Now, when h is small enough, g of a plus h is very close to g of a, which is what we will use, right? Same thing here, delta 2, when you have g of a and g of a plus h, notice g of a plus h is not 0 as long as h is small enough. So, this really doesn't affect anything, and delta 2 divided by norm h goes to 0, right? So, that's roughly the proof, but to be a bit more precise, right, let's do this in a bit more precise way, right. So, this is less than by the triangle inequality. So, as I said, the triangle inequality is our best friend. We will keep using it often, okay, even without mention sometimes, right. So, what do we have here? We have the derivative times h divided by norm h times g of a and 1 by g of a plus h minus 1 divided by g of a. This goes to 0. This stays bounded. Why does it stay bounded? Because norm of g of a plus h, in fact, why bother with bounded? This, as h goes to 0, goes to 1 by g square of a by continuity. Recall that 1 divided by g is continuous at a point a where g of a is non-zero, right? So, this times this goes to 0, okay. These cancel out. Again, by continuity, this goes to 0, right? And this remains fixed. So, the product of these goes to 0, okay? And so, we are done, right? Okay, so that means by the sandwich rule, by the sandwich theorem if you wish, or the squeeze rule or whatever you want to call it, this goes to 0 as h goes to 0, which proves what we want, right? Right, so let's do a couple of more properties. So, if f is constant, obviously the gradient of f is identically 0. This is trivial, right? The conversely, if U is a connected open set, and f is differentiable, then f is a constant. Recall that without the assumption of connected open, this is not true even in one variable calculus. So, it can be different constants on different intervals, right? All right. So, it appears we are out of time. We will continue proving this the next time. Thank you for joining.